Pooling the variance for the pooled variance t-test, also known as the equal variance two independent sample t-test. Let's do a little warm-up exercise first. You should know that the sample variance is equal to the sum as I goes from 1 to n being the sample size, of xi, which refers to the ith observation. Let me write this down for you. ith observation, minus the sample mean, quantity squared, divided by the sample size minus 1. Now, the ith observation is an indexed way to represent the first observation, the second observation, the third observation, the fourth observation, all the way up to the last observation. So x sub 1 is equal to the first observation. X sub 2 is equal to the second observation. X sub 3 is equal to the third observation. And we take this pattern all the way up to x sub n, and we actually read this as the nth. N with a th, really, this is how it's read, observation. And the general observation is actually called the ith observation. Now, this is called summation notation. You may be familiar with it if you're up to this point, but I'm going to review how this works anyway, just so that you completely understand this. So this summation notation actually comes from the 18th century when calculus first started really appearing on the scene of our people. And what it is it's sort of like computer code, only it was meant for humans and not computers. But what it says is you start off with this index, I, and it's like I equals 1, take the first observation, subtract the mean, square it, save it in a memory location, and then I equals 2, take the second observation, subtract the mean, square it, save it in a memory location, I equals 3, take the third observation, subtract the mean, square it, save it in a memory location. Do this all the way until you get the last observation, square it, subtract the mean, square it, save it in a memory location, and then you add up all those terms that were saved up in the memory location. And this is the sum. Now, this numerator happens to be called the sum of squares. And we use SS in statistics to represent the sum of squares. And the sample size minus 1 happens to be the degrees of freedom. So this estimate of variance of this population is actually the sum of squares divided by the degrees of freedom. Now, this is an important idea when you're going into sort of the end of Stats 1 and the very beginning of your second course in stats. If you're ever going to study a topic called analysis of variance, which is absolutely necessary for fields like sociology and psychology, this idea of the sum of squares will figure prominently in analysis of variance. So in this warm-up exercise, what I'm asking you to do is solve for this numerator, which is the sum of squares. So all we do is we multiply both sides by n minus 1. So one little step takes us from the definition that s squared is equal to the sum of squares divided by the degrees of freedom to the fact that n minus 1 quantity times s squared gives us the original sum of squares. And this is a famous statistical formula, super, super important if you're ever going to go into psychology and take analysis of variance. So this has to be memorized, right? It's just one little step in algebra, right? The degrees of freedom cancel, and you're left with the original numerator, which is called the sum of squares. So that's your warm-up exercise, and don't proceed to the next part of the video until you can actually do this yourself and you understand two things. One thing you have to understand is that the sample variance is equal to the sum of squares divided by the degrees of freedom. That's the first thing you have to know. And the second thing you have to know is if we multiply both sides by the degrees of freedom, they will cancel, and we have the degrees of freedom times the sum of squares, times the sample variance is equal to the sum of squares. And the degrees of freedom is n minus 1. So we have n minus 1, s squared equals the sum of squares. Super important. Don't go on in this video until you know this. Okay. So once you have this warm-up done, now I'm going to show you pooling the variance for the pooled variance t-test, also known as the equivariance to independent sample t-test. So in this case, let's assume we have two groups, because this is called the two independent sample t-tests. So we have two groups that we're interested in. Group 1, which we're going to call x subscript 1, because 1 is the first group, is a normally distributed population with mean mu1. There's a little 1 here. This isn't a comma, so this is a 1. And the 1 is because it's in group 1, with variance sigma squared. And group 2 is also a normally distributed population, and we're going to call the mean of this population mu sub 2 because it's group 2. And I want you to notice that this has the same population variance, and that's why there's no subscript here. So make sure before you go on with this video, you really get this idea, because you're getting into a more advanced area of statistics if you're up to this, right? There's no subscript here. So that means the variance is the same, the population variance is the same for both groups. Now, the pooled variance is used when we have the pooled variance t-test, which typically tests the null hypothesis that both population means are equal, which is the same thing as saying there's no difference. Remember, subtraction is difference. So saying the two population means are equal is the same thing as saying there's no difference between the two population means. That is, the difference equals 0. Okay, the alternative hypothesis can be a left or a right or a two-tailed test, just like you've done in your previous hypothesis tests. If you've never done a hypothesis test, you're in absolutely the wrong video. You're way over your head. This is a more advanced level of statistics. Okay, so what we're going to do is we're going to use samples from both groups. Now, these have to be random samples, and they have to be independent random samples. So the groups have to be sampled randomly and independently. And this sigma squared, which is called the common population variance because it's the same in both groups, is estimated by a very interesting estimator, which is called the pooled variance estimator. And what is it? Now, this is why I had you do that warm-up exercise, because without this warm-up exercise, this is going to look like just a group of symbols that will mean nothing to you. But with the warm-up exercise, this n sub 1 means the sample size from the sample of the first group. And this is the sample variance from the sample from the first group. This is the sample variance from the sample from the second group. So what are we doing here? From the warm-up exercise, we're getting the sum of squares from the sample from group 1, and we're adding that to the sum of squares from the sample from group 2. That's why there's a subscript 1 here and a subscript 2 here. And so here we have all of the sum of squares from both groups. This here is the degrees of freedom from the first group. So I'll call it df subscript 1. And this is the degrees of freedom from the second group. So this pooled variance estimator is the sum of squares from both groups divided by the degrees of freedom from both groups. And this is super important if you're ever going to want to go into a field like psychology and study analysis of variance. This is called the pooled variance estimator. And some people will simply call it S squared sub P. I'm going to write that down. S squared sub P, which means the pooled variance estimator. Now, when would we actually... Oh, here's a little remark, though, that I do want to get through. In the warm-up exercise, you verified the fact that n minus 1 s squared gave you the original sum of squares. So that's really important, because what do we have here? Here we have n1 minus 1 s1 squared. That's the sum of squares from the first group. And here we have n2 minus 1 times the sample variance from the second group. Sum of squares, degrees of freedom. That's how it works. So I want to give you this in one piece of paper. I want to give you this. This sort of puts it all together. And I would recommend pausing the video and actually taking a screenshot of this. If a formula sheet is allowed on your final exam, you know, I always let my students use formula sheets, but not every instructor does. But if a formula sheet is allowed on your final exam, definitely take a screenshot of this and write it out in careful detail. But I want to explain what it is. So here, this first expression, n sub 1 minus 1 s sub 1 squared plus n sub 2 minus 1 times s sub 2 squared, this is how you get the sum of squares if the sample variances have already been calculated for you, which most likely on a final exam, unless you want your students to spend hours and hours and hours with raw data, most likely you will give your students already calculated sample variances, and they'll have to use this for the numerator. But some professors may want to see you do this from the absolute beginning, and they might only give you like 4 or 5 observations, and they might want to see your attention to detail to see if a student can actually crank this thing out with raw data with like 4 or 5 observations and get the right answer without making a single mistake. That's important to some professors. It's the idea of attention to detail. So if you have the original observations, then you're going to have to use this numerator. Now I want you to notice here that this is x sub 1 I, and this is x sub 2 I. So this indexed variable represents the first observation from group 1, the second observation from group 1, the third observation from group 1, the fourth observation from group 1, till we get to the last observation. And notice this is n sub 1. This is the sample size of group 1. Notice how this is indexed. Then, if the professor really wants to see you go through this with raw data, this indexed variable represents, since it's x sub 2I, this is the first observation from group 2, the second observation from group 2, the third observation from group 2, the fourth observation from group 2, all the way up to the last observation. And notice there's a subscript 2. That tells us it's from group 2. This here is the sample mean from the first group. That's why there's a subscript 1. This here is the sample mean from the second group. That's why there's a subscript 2. And we square all these deviations to get the sums of squares. And you would only use this formula if your professor gives you raw data and really wants to see that attention to detail thing where you actually do it with raw data. Now, I personally wouldn't do this. I would give students a question with raw data just to calculate the sample variance, but that would be it. And that would be one question. And then when I get them to pool the variance, I would give them the summary stats to have them do that, because, I can't really imagine, making a student do this whole thing with raw data on a final exam. But on a homework problem, absolutely, definitely. On a project, absolutely, definitely. Although statistical software does this. So that's how you do it. Now, I want to emphasize an idea here which students are going to have to deal with. It upsets me that students have to deal with it, but students have to deal with the fact that some textbooks are steaming piles of crap. Now, proper use of summation notation, you have an index, which is usually I, J, or K, and it says I goes from some lower limit of summation to some upper limit of summation. And it's crystal clear what it's doing. And that's what we did before. We had that, right? We were very, very clear here. Here I goes from 1 to the sample size in the first group. I goes from 1 to the sample size in the second group. Everything is indexed. It's crystal clear. And this is proper use of summation notation, but it is difficult to typeset. And some textbooks don't want to go through this work. So in crappy books, you won't see the index, you won't see the lower limit, and you won't see the upper limit, and it'll look something like this. This is crappy, and it confuses students. Yes, it saves a little effort on typesetting, but for a $200 stats book, I don't see why they can't use proper notation. So in your textbook, if it's crappy, you might see something like this. Crap. This is good. So what I always encourage students to do, I used to do a lot of tutoring. I don't tutor anymore at all. I make these videos instead. But I used to do a lot of tutoring. And when I did private tutoring, I always had students put the index in and the limits in. But I haven't done that since graduate school, which admittedly was about 20 years ago. So if any private tutors are listening to this, make sure your students always put these limits in. So the next thing a student is going to ask is for an actual example. And so now I'm going to show you where we would actually use such a thing. A politician wishing to save money on education by decreasing the number of teachers conducts the following study on reading scores of 8th grade students. She randomly samples students from classes meeting 5 days per week, regular teaching, Group 1, and students meeting 2 days in class and 3 days online, Group 2. She wishes to test whether there is a significant difference in reading score improvement at the end of the semester at the 5% significance level. Of course, the politician probably wants to do this because the politician probably wants to show there's no significant difference so the politician can fire teachers. So if we were to conduct an actual equal variance t-test to test whether there was a significant difference, and we were to use the equal variance assumption, which would allow us to do this by hand rather than using statistical software, we would need to be able to compute the pooled variance estimate. And so let's actually do this with an example. Here we have some actual numbers, so I'm going to show you exactly how to do this. So notice in the regular teaching, 5 days a week, which we call Group 1, we have a standard deviation of 8.02. Now, when we have data like these, this is a sample standard deviation, not a population standard deviation, because it comes from actual observations. And here we have the standard deviation, again, the sample standard deviation, from Group 2, which was 2 days in class and 3 days online. Now, this is hypothetical data, but you can see probably how this could come about in the real world quite easily. Now, n is the sample size in each of the two groups. So we'll call this Group 1, we'll call this Group 2. The next step is just to write down the formula. So remember, the pooled variance estimator is given by n sub 1 minus 1 s squared 1 plus n sub 2 rather, sorry, n sub 2 minus 1 s sub 2 squared. So this is the sum of squares from the first group. This is the sum of squares from the second group. Remember, this is the sample size in the first group. This is the sample size in the second group. This is the sample variance in the first group. This is the sample variance in the second group. Now, any variance estimator has some kind of sum of squares divided by degrees of freedom. So the degrees of freedom in the first group is n sub 1 minus 1, and the degrees of freedom in the second group is n sub 2 minus 1. So here's our formula, just as we wrote it. And now all we have to do is plug in the numbers. So n in the first group is 11. 11 minus 1 is 10. So this is equal to 10 times, and in the first group, the standard deviation is 8.02. So we have to take 8.02 and square it to get the sample variance. Remember, s squared stands for the sample variance, which is the square of the standard deviation. So the number in the second group is 15, that's the sample size. So 15 minus 1 is 14. And 14 times 10.57 squared and we divide this by 11 minus 1, which is 10, plus 15 minus 1 is 14. 10 plus 14. And notice there's a 10 over here, there's a 10 over here, there's a 14 over here, there's a 14 over here. That's no accident. I hope you can see that's always going to be the case. So let's put this into the calculator and actually see what we get. So we hit the parenthesis key and we go 10 times 8.02 squared button plus 14 times 10.57 squared button, close parenthesis, divided by, and 10 plus 14, of course, is 24, equals button, and we get 91.973, which is the pooled variance estimate from our two independent random samples under the important assumption of equal population variance.